think like that every recording like correlated it doesn't define the movement of the grapes. Actually, I just thought of that just now.
I still like the grapes there also.
My grandma had grapes at her house. She's passed away and we sold the house. We don't have any of it. It's not like you buy a house and like sinking, not sinking, but it's sinking somehow into it. So I think we're gonna go. Yeah. But like when you take, I tried to research it. It was really, so you want to take one that takes normal time. Okay.
Yeah.
So would that be like November is the time to get things? You know, they looked at March's house. That'll be good for speeds.
It's a little bit too far. Krista, can I ask a question about the take home, please?
Like an answer to it, or like how to solve it, or just like a general?
Just a general question about number one. So, I guess I just moved it. Okay. Is that asking for, not for the solar solubility? Excuse me, the molar solubility? It's not asking for the molar solubility?
Well, it is, but then it's asking it right in grams per liter.
I see.
It's too bright. All right, let's go ahead and get started. So how was Earth Day? I looked at the posters. The posters look pretty awesome. I have them graded. I just didn't input them yet. There's a few straggling pieces. So some of you emailed me or posted your like works cited on the posters. That was awesome. There are a few groups that I couldn't find sources for, so I kind of left it blank for now. So I'll probably hunt you down probably in lab tomorrow so I can finish grading these. But overall, again, excellent job with the posters, really pleased. And then if you saw, they've ended up on the wall over there so everybody can see all your hard work. And so now So thanks again for Earth Day and for doing the posters. And so just to remind you, so we have our midterm next week. I know, this is already week 4, next week is week 5. So that's exciting, hopefully. And so we'll do our review on Tuesday like usual, and then take the exam during class on Thursday. And of course, with the time extending to recitation. And then there'll be no lab next week. So just give you plenty of time to focus on your exam. And then we will have lab this week. Let me at least put that out for you. I need to make it live on the Blackboard. Okay, I have so many papers. So homework, I'll leave this out front. And then this week we'll be doing activity series. So I'll leave this up at the front as well. And then please make sure you turn in your quizzes. So thank you to you that did. And then I'll take homework and anything else. All right, any other questions, anything we need to chat about before we continue? And so probably regarding last week's material, we didn't do too much review on that, like with the math. So my plan is to hopefully hit that either Thursday, if we have time with the oxidation reduction chapter, or that'll be kind of priority for Tuesday review of what math we need to know. And then if you're in the chat, say hello. I think I have a few people in the chat today. Just want to know you're there. All right. Let's go to oxidation reduction reactions. And have we briefly talked about oxidation reduction? I feel like we might have touched on it. Yeah. So we kind of remember oxidation react. So we'll say recall from last term, or maybe first quarter. And so we notice these types of reactions, especially like the copper reaction. Do y'all remember kind of that lab? So you started with like pure metal copper, and then it dissolved. And so if you remember that, those steps, especially where you did the single replacement, those were considered oxidation reduction reactions. But again, we'll go in depth. So I'll put there, single replacement reactions tend to be some examples. And then, of course, combustion reactions tend to be our classic example of oxidation reduction reactions. And so let's define what is an oxidation reduction reaction. And so these are any reaction in which electrons are transferred from one atom to another. And so that's going to be called redox. So usually you just see the term redox reaction thrown out. And so atoms that lose electrons are being oxidized, and atoms that gain electrons are being reduced. So if we go back to our classic example, so sodium metal plus chlorine gas reacts together to, of course, make our table salt, sodium chloride. And so if we kind of remember, again, I think this is kind of first quarter stuff, where we mentioned, well, sodium tends to be in the 1+ oxidation state, so that means that it gives up electrons. And so now we can, again, tie all that together now. So if sodium is losing electrons, that means it's being oxidized. And we see that a lot, right, where the metal is in that positive oxidation state, showing that it's giving up those electrons. So metals tend to undergo oxidation. And then we have, of course, our chlorine then. We know that chlorine wants to gain an electron, and so it is reduced to make that chloride. And so other terms will kind of crop up, and so let's add those now. And so sodium metal, again, it was oxidized because it's providing those electrons, but many of these metals, especially, so, you know, sodium and potassium are really key. And so they're called reductants. So these are going to be, if your metal is being oxidized, then it's also called a reducing agent. So these terms can be used interchangeably. And so again, reducing agent just means that it's supplying the electrons. And then reduction, if it's being reduced, it could also be called an oxidizing agent. So you might have to identify that. And so of course you can identify it. So oxidation is a process that occurs when your oxidation number of your element increases, and so that means that you're losing electrons. But other ways to identify it, especially in like combustion reactions, is if it undergoes oxidation, it tends to add oxygen and lose hydrogen. So kind of like, right, your carbon, if it's like methane being combusted, it goes from CH4, becomes CO2, so you can tell that it's being oxidized. And then we'll look at what this means more as we go in depth, but a half reaction that has electrons as products. So again, if oxidation is losing electrons, that means that if you write your half reaction for that process, you have to have electrons produced as part of that process. And then, so reduction is kind of the opposite then. So then your oxidation number would decrease. That means you're gaining electrons. And then more generally, you can see that it might lose oxygen and gain hydrogen. And again, your half reaction then would now have electrons as reactants. So if it's being reduced, right, you have to add electrons to it. So that's going to be the reactant. And so where we're kind of going with this is you can kind of see these half reactions. And so we'll have to balance them. And so that'll be kind of the big key point in this chapter, is however many electrons are going in to oxidize, that has to be the same number that were reduced, so they balance out. And so what we were saying is kind of the easiest way to look at these reactions is to split them into what's called these half reactions. And so any redox reaction you can split into their two separate half reactions. And again, with your oxidation reaction, has your electrons as products, and your reduction reaction has your electrons as reactants. And so how would we do this? So we can look at our example. And so we have this overall reaction of chlorine gas plus iodine plus water gives us chloride plus iodate plus H plus ions. And so here are the oxidation states. So let's go through this analysis and make sure we remember how to assign oxidation states. So do you remember, why do they put a 0 for chlorine? What was the rule on that? Do you remember? I think I had some. Here we go. Let's do this, since everyone gave me a blank stare. So let's look at this quick refresher. Add this to my notes. Oh, okay, one more time, sorry. All right, so I've got these rules back. So this is just a refresher. So you should know this, you should have seen it, but in case we have forgotten. So these were our rules to kind of determine oxidation state. And so remember, like fluorine is always -1. You kind of remember that from your group 7. Remember, oxygen is always -2. You kind of start with those. And then obviously the exceptions were peroxides, if you kind of remember that. So example, H2O2. So this is just hydrogen peroxide. But then if we balance this, so we know hydrogen has the 1+ oxidation state. But that means that this O2 in total is 2-, which means each oxygen is only -1. So that's kind of weird, but that's only peroxides where it becomes -1. And then, oh, this is a rule that I was referring to. So the oxidation state of an atom in its elemental state is 0. So do we remember that now? Does that sound familiar? Fuzzy, maybe? And so going back, so that's why they have a 0 here. So we have chlorine elemental form. I'll just rewrite it, so that's 0. And then of course we have our iodide ion here. So it has a negative charge on that, so that means, right, it's in the -1 oxidation state. This would be the same thing as if it's paired with like a counter ion, so sodium iodide. So don't let these charges kind of confuse you. And then, did you have a question?
Yeah, well, how do you know the CO2 is in its elemental form? Like, why is that one in its form and then that one in its form?
And like why is this in its form, but then iodine is not?
It's because it's negative?
Yeah, so this is implying that it's like with something, so I kind of put a counter ion, so it might look like more familiar to you. But it's just when they start doing these half reactions, they ignore, ions that don't undergo oxidation. So if it's just like a counter ion sitting here, like sodium, and nothing happens to it, they just kind of ignore it. So yeah, so that's what that's referring to. And so yeah, with the elemental form thing, you kind of have to remember which ones are your diatomics again. And we can always highlight those if we need a refresher on the diatomics. Do we remember our diatomics, Elise? Okay, I see mixed reviews. Let's find a periodic table. Oh, no, I can't find a periodic table. There we go. So when we're talking about elemental forms, so I'll highlight the diatomics. So remember that was hydrogen, and then the rest make that like little 7 pattern. So nitrogen, oxygen, fluorine, chlorine, bromine, iodine. So all of these, right, their elemental form has to be the diatomic. So that's going to be just the oxidation state of 0. Don't forget the weird ones too, like P4, that's its elemental form. S8, also elemental form. So kind of all those allotropes that were funny. That was kind of first quarter. I know. That's the problem with chemistry, but cumulative by nature. So everything's kind of coming back. But ask questions, keep asking questions. And then so we go through this. And so, of course, right, hydrogen, group 1. So that's going to be 1+ for its oxidation state. We said oxygen's always 2-, and it's group 6. We can always look at our periodic table. So again, just a refresher, right? Write your oxidation states. And remember the switch happens there, so +4, -4. And then generally most common, -3, -2, -1. And of course, your noble gases, generally 0. And so once you get kind of your reactants, then you want to compare the oxidation state of the products. And so again, just finish writing them over. So now it became chloride. The counter ion doesn't matter. Again, this could be potentially sodium chloride, but we know now it's in the -1 oxidation state for chlorine. Then we have this IO3 -1, our iodate. And so this could be confusing, but let's just break it down. So we know oxygen is always -2 for the oxidation state. It has an overall charge of -1, so you could set up, your mini algebra here. And I'm just using iodine, so whatever the ox state is, you could use X. I'm just using I for the variable, plus 3 times -2. And then you can solve for the oxidation state of iodine. So then what's the oxidation state of iodine in this compound? So 5, so that's how they got that number there. And then oxygen, -2, just writing it. And then hydrogen, so now this is just an acidic solution or something. And of course that's just 1+. All right, so now you've kind of written all this mess out. So let's see, well, how do we separate it out? And then we'll have to figure out how to balance it. And so the first thing we want to identify, well, which ones even change oxidation states? Let's start with that one. So which ones have a change in oxidation states? So I hear chlorine and iodine. All right, so now we can start separating that out. And so you want to identify what's changing, and then you can start pulling out the reaction. And so the next step would be to identify, well, who's being oxidized and who's being reduced. And at this point, so sometimes I like to just draw little arrows, kind of indicating what's going on. And so we have chlorine going from 0 to -1. And so what does that mean? Is it gaining or losing electrons? So gaining, since it became more negative, good. And so I can put there gaining, and then it's 1 electron per chlorine. But then we'll notice that, of course, we have 6 of them, so this is going to be a 6-electron process there. And so they didn't write it balanced here, but I would probably write what's being reduced. And then at this point, you can start separating it out. And so you could put, I'm going to stick with the 3 equivalents of chlorine, because that's what's shown here. So I would write 3 equivalents of chlorine gas. And then again, you want to identify, so each individual atom of chlorine is gaining 1 electron. But since it's 3 times 2, so there's 6 of them, so it's going to be plus 6 electrons to give us now 6 equivalents of chloride. So there's 1/2 reaction. And then we have, so we said our iodine was oxidized, and so let's look at that. So it went from -1 to +5. So each individual iodine is then, of course, losing 6 electrons. And so then we can write that process out. So oxidized. And this time, again, just following from our equation. So 1 equivalent of iodine gives us our iodate. And then now we have to put our plus 6 electrons in our product. Again, showing that we lost 6 electrons. And so if you look at the example, obviously theirs is unbalanced since they didn't take into account the 3. I went ahead and again wanted to just write what was shown here. And in this case, right, they are balanced. So this is good. And that's something that you're looking for. So when you're balancing these types of equations, that's always the first step is, are my electrons balanced? And of course we see, right, 6 electrons in our reactant, 6 electrons in our product. So they would, of course, cancel each other out if we were to add these two half reactions together, and that's good. That's exactly what we want, right? We have to gain whatever we lose, so they're just being transferred. That makes sense? Any questions so far? And then, so we'll figure out, again, as we dive deeper, what to do with the water and the 6 little hydrogens here, so that'll be kind of balanced out depending on the reaction conditions. And so that's what we'll practice in this chapter and what we're working on. And so we'll have our half reaction method, so we break down our reactions into their half reactions, and then we balance our electrons and for the atoms, and then of course the 2 half reactions are adjusted at the end so that your electrons are equal. So now it's similar to balancing equations, right? You've done that before, so now you'll balance the equation and then you'll balance it again with the electrons, or make sure the electrons match up. And so this is kind of the steps, and again, we'll go through this all, so don't feel too overwhelmed by all this. This is just outlining what we're going to do. So again, you'll assign oxidation states. That's always step 1. Figure out who's being oxidized, who's being reduced. Do our half reactions, and then balance it. And so you'll see what I'm talking about when it's talking about acidic or basic conditions. So first you'll balance everything else other than hydrogen and oxygen. Then you can add water if you have excess oxygen. And so again, we'll go through this process together and see how this works. Then after you balance out the oxygens, you can add H+ where H is needed. And then at the very end, if it's done in basic conditions, and so the reaction will say, like, this is done in acidic conditions, this is done in basic conditions. And so that's how you know what to do. But then at the very end, if it's a base, you neutralize all your H+ with hydroxide, and so you'll add the appropriate hydroxide to both sides. And then at the end, you'll adjust your electrons, and of course add your half reactions to get your overall equation. All right, so that was a lot, but we'll go through that, like I said, step by step. And so we have our first example. So it asks us to balance the following redox equation, and we're in acidic solution. And so we're given aluminum plus copper 2+ gives us aluminum 3+ plus copper. So at least just take a few minutes. So I'm not expecting you to go through the whole process, but identify the oxidation states at least, see who might be getting oxidized and reduced, and then we'll kind of go from there. Oh, and also I forgot our fun little mnemonic so you can remember oxidation and reduction. So there's two different ways I say you can remember it. So there's either oil rig, which I'm from Texas originally, so this is what I grew up with. But this is oxidation is losing electrons, and reduction is gaining electrons. So that's one way. Now, if you're not a fan of the fossil fuel industry, or maybe you just like cute, fuzzy cats more, you can always do this Leo goes grr. And so I used to teach for a school where the mascot was Leo the leopard, so I changed this to Leo the leopard goes grr, but it could be Leo the lion or whatever your favorite fuzzy cat is. But that just stands for, so of course, losing electrons, oxidation, and gaining electrons, reduction. So either one, whichever one you want to use, but I recommend it, just slap it on your paper before the exam so you can always remember which is which. So now looking at this one, well, we only have so many options here. So what's our oxidation state of aluminum to begin with? So it's +3 after the fact, right? Because remember, it's only +3 when it's in like a compound. But then if it's by itself, solid, so what's that going to be? 0, exactly. So elemental form hasn't done anything, just a nice chunk of aluminum there. And then, so of course, what's our oxidation state of copper? So it has a little charge on it, though. So when it has that copper 2+, remember it's signifying it's in some sort of compound. We don't care what the counter ion is. So it could be, copper chloride probably or something like that. But that 2+, right, that also matches the oxidation state. So that's what it's also telling us. So it's copper 2+. And so it's aluminum then in the product. So 3+, and then what's copper? 0. Perfect. And so let's see. So aluminum, is it gaining or losing electrons? So losing, and it looks like this is a 3-electron process here. And then what about copper? So it's going from 2+ to 0. So now gaining, and now it's 2 electrons. So we might have to do some balancing later. But now let's just start with our step 1. And so is aluminum being oxidized or reduced? So oxidized, so it lost electrons. And so now we can write out just our half reactions. So aluminum solid goes to aluminum 3+. And of course it lost 3 electrons. So that's part of our product here. And then we can just write it next to it. So we have our 2 half reactions. So that means our copper was reduced. Of course, it went from copper 2+, and now we need to put our electrons in the reactant. So +2 electrons gives us our copper solid then. All right, so now we're here. And so first step, balance out our atoms, but everything's already balanced, right? 1 aluminum, 1 aluminum, 1 copper, 1 copper. So we don't need to change anything there. But then, what do we need to fix? So what's not balanced? Yeah,
There's an extra electron in the aluminum reaction.
so our electrons don't match. So what can we do to get them to match? Also trying to think of like our least common multiple maybe. We remember those math terms. Yeah,
We balance the reaction, so we're timesing the aluminum oxidation reaction by 2 and the copper reaction by 3. That would balance everything else.
excellent. So let's do that. And so first I'm just going to rewrite it. So 2 equivalents of aluminum then. Now it gives us 2 equivalents of our aluminum 3+, plus now 6 electrons. And then let me rewrite our new reduction reaction. So 3 equivalents of copper 2+, plus 6 electrons give us 3 equivalents of solid copper. And so now at this point, everything is balanced. So we're good to add. So now we can say, right, add our 2 half reactions. And I'll do this really explicitly for now, so I know it's kind of simple, but I'll just rewrite what we did so far. And so now we just want to cross out whatever's the same on the reactant and the product side. So that means our electrons cancel out, which is good. That's what we want them to do. And now we can just rewrite it with everything on the same lines. Of course, all the reactants on one side, all the products on the other. And so then that gives us, right, 2 equivalents of aluminum solid plus 3 equivalents of copper give us 2 equivalents of aluminum. Oh, and I dropped my 3 plus 3 equivalents of copper. Does that seem relatively straightforward? So go ahead and try this one now and see if you can do it all the way writing out the balanced equation. So I'll give y'all a few minutes to work on that and we'll go over it. How's our equation going? I see some thumbs up.
I think I have an answer. I don't know if it's right.
Yeah, walk me through it. I wish we had, I've been trying to get this. It's like, I want a whiteboard that I can display and hook up, but it's so expensive. I'll try to figure out a workaround. I'm trying to.
First started by balancing the two half reactions, and I got 2H minus.
Or H plus. I think
Oh.
you just said the wrong thing.
It has it in the thing as H minus.
Oh.
Yeah, 2H. Mine prints out had H minus for some reason. So.
Oh, I don't know if maybe the plus sign got lost.
Yeah. So my answer is wrong now.
Oh.
Never mind.
Well, you were on the right track,
Yeah.
but let's hear. So we had 2H plus.
Goes to, so this would be that plus 2 electrons would make it go to would make 1H2.
So that looks good. So everyone got this half reaction. And then we can say, right, our hydrogen is being reduced, so we'll identify that.
And then chromium, or CR, which I forget.
So then chromium.
Chromium goes to plus 2 electrons plus chromium plus 2.
And then, yeah. So that's good. So then you had 2 electrons as your product. So chromium goes from 0 to 2 plus. And of course, oxidized as it's losing electrons became more positive. And then in this case, well, they were both 2 electrons, right? So we don't need to worry about balancing that. We already balanced the hydrogens, the chromiums were balanced. So at this point, we just need to add them now. So add together. And again, I'll just kind of rewrite it first, just really explicitly so we can see all our products, all our reactants. And again, now we're seeing, okay, we have our 2 electrons on our reactant side and our product side. So that balances, leaving us with our overall equation. So 2H plus chromium gives us hydrogen gas plus chromium 2 plus. So do we all get that? Do we have questions? Do we figure out what went wrong if we didn't get there? Oh, I'm sorry. I don't. Yeah, I can see it on my printout. I don't know why. Yeah. I apologize. All right, let's try a different scenario, but we might have to walk through it together. So let's start walking through it. So now we're in a basic solution. So let's first write the oxidation states of all these elements. So actually take a minute or two and just figure out the oxidation states, and then we'll go over it, and we'll go over the rest together. So just identify oxidation states, maybe who's being oxidized, who's being reduced, and we can talk about it. And this should be, if you're looking at the PDF handout, it should be I minus MnO4, -1, then just I2, and then MnO2, so no charges on those. So let's look at our oxidation states. So what do we get for this first iodide here? Yeah,
Got -1.
so -1. And remember, all that's just saying is it's probably in some compound, sodium iodide or something. They're just not bothering to show the counter ion there. And so let's see, if we have this manganate O4 species with a -1, so let's start with our oxygen, because we always know what oxygen is. So what's the oxygen oxidation state? -2. And so if oxygen is -2, and the overall charge is -1, what's our manganese oxidation state? So +7. And now moving over to our products, so what's our iodine?
0.
So 0. So again, elemental form. And so now we have this manganese oxide species. And so of course oxygen is still -2. And what does that make our manganese? So +4. So now we can identify what's going on. So manganese, we go from +7 to +4. So is it gaining or losing electrons?
Losing electrons. It's gaining electrons.
So gaining electrons, so we can say each one gains 3. And then if we go, so now iodide to the iodine, so is it gaining or losing electrons? So now losing electrons, so we'll have to balance that out. So right now we don't even have the correct number of iodines. So I'll leave that alone for a second, because we're going to have to do at least some atom balancing first. So then let's separate them. And so right away I'm going to go ahead and slap a 2 in front of this iodide, since I know I need 2 of them. And so if there's 2, that means I'm losing 2 electrons then. So I2 plus 2 electrons as my product. You can see this is oxidized then. And then our other half reaction, then we can write our MnO4 species goes to MnO2, and we need to add our plus 3 electrons. And so now let's continue balancing. So this one's fine, right? We dealt with that. And so now we have to deal with this manganese oxide species. So what do we need to do to balance out the oxygens? Do y'all remember what the steps said? Exactly. So in case you didn't hear, add water where you need oxygen. And so just looking out, again, our manganese is balanced. That's fine. But I have 4 oxygen versus 2 oxygen. So what should I do then if we need to add water? So how much water should I add and where? So on the product side. And then we need to add 2 of them, right, to give us our 2 oxygens, so 2 equivalents of water there. And it's now just double check here that we have our oxygens balanced and our manganese, so that's still balanced. Then 4 oxygens, and now 2 plus 2, so that gives us 4 oxygen. Now how do we deal with the hydrogen? What can we add? OH, or so we will need to add OH eventually, but there was kind of a step in between. So we added our oxygens. Now we need to balance our hydrogens. Exactly. So we can add H plus, and we can flip back together to these rules so we could follow along. All right, so we said, okay, we added water when oxygen was needed. We did that. Now we need to add H plus where we need hydrogen. So let's go back and do that. And so we're just missing 4 hydrogens, right, from our reactant side. So we have 4 over here. So now I'm going to add hydrogens. So plus 4 H plus, and of course plus our electrons. So now we're here. And so if we were in acidic conditions, I'm just going to add a note. So could stop here for acidic. And this is where those conditions matter. So if we were in acidic conditions, right, that's saying you have excess H plus. That's the definition of acidic. So you wouldn't need to continue. But this case, we're in a basic solution. So that means we're going to have excess hydroxide instead. And so we flip back over to our little kind of cheat sheet. Now it says if the reaction is done in a base, we have to neutralize that H plus with hydroxide. And so all that means is we're going to add hydroxide to both sides so that we cancel out the hydrogen here and make water, and then of course have hydroxide. And we may have to do some water balancing at the end. So let's just do that step. And let me make some space here. So now plus 4 equivalents of hydroxide, plus 4 equivalents of hydroxide to keep that balanced. And so now I'll rewrite it. So now we have our charged manganese oxide species. Now we make plus 4 equivalents of water. So we just did the neutralization. Still have our 3 electrons. And that gives us our manganese 4 oxide plus 2 H2O plus 4 hydroxide. All right, so now we're here. And so let's stop here. And so now we need to balance out. What do we need to balance out next? What did you say? The electrons, exactly. So now we have this taken care of for now. But you notice we have a discrepancy in our electrons. So what can we do to fix this? Perfect. So let's do that, and then we'll get to the adding part and all that. So first I'm going to rewrite our oxidizing portion. Let me zoom out for a second. So now 6 equivalents of iodide gives us now 3 equivalents of iodine plus 6 electrons. So that's looking good. Now we have to do this times 2, just like you said. So now 2 equivalents of our manganese oxide species plus, so now 8 H2O plus 6 electrons gives us 2 manganese 4 oxide species plus 4 waters plus 8 hydroxide. So now everybody's here, right? And so now we just need to cross out what's the same on both sides, get rid of our electrons, and also get rid of some of these waters. So if I have 4 water on our product side and 8 on our reactant, I can go ahead and cross out all those, and then that leaves us with 4 H2O. Our electrons cancel, so that's good. So now we could just write the overall reaction. Oh, I guess I have allergies today. And so now I'll just rewrite the whole overall reaction. So all our products. So 6 equivalents of iodide plus 2 equivalents of our manganese oxide charged species plus 4 equivalents of water gives us 3 equivalents of iodine, 2 equivalents of our manganese 4 oxide, and then leaving us with our 8 equivalents of hydroxide. So any questions about the process on that one? So, a little tedious, but always just show your work step by step. And, for exams and everything, as long as I can kind of at least follow along with your train of thought, I can always give you plenty of partial credit or anything. So let's turn you loose for a little bit on this one. So take maybe 4 minutes or so to get started, or we'll see how far we get. And so it's in a basic solution. So just start it, get as far as you can. If you can complete it all the way, awesome, but if you get stuck, that's always good, so then we know what we need to talk about. Oh, and I think this is a typo or something. This is supposed to be, by the way, the chlorate. So that's ClO minus, not like CIO, which it kind of looks like. I think that L just looks funny. And then, yeah, just so everybody knows, that's a -1 charge, -1 charge overall, -2 charge overall, -1 charge. In case it got lost on the PDF version. All right, so let's hear what you've gotten so far. So let's just go through these oxidation states. So what did you get for the oxidation state? Let's start with this oxygen in this chlorate species. So what's the oxidation state?
Is +1.
For the oxygen?
Oh, for the chlorine. -2 for
So -2, so it sounded like then if this was -2, you got +1 then for the chlorine, you were saying? All right, excellent. 1 plus, oh, that was a really weird one, sorry. And then, so now, there's a few different ways to analyze this. So probably the easiest is if you just treat the hydroxide as a whole. You know, this whole polyatomic has a -1 charge overall. Then this whole chromate hydroxide species has a -1 charge. So what does that make the charge on chromium?
+3.
So +3. And then what's the oxidation state on this chromium now in our product?
+6.
So +6. And so oxygen, -2. And then what's our chlorine here? So -1. All right, so we can at least identify. So chromium's going from +3 to +6. So is it gaining or losing electrons?
Losing electron.
So loss, so we'll do lost 3 electrons for each one. And then chlorine went from +1 to -1. So how many did it lose or gain?
It gained 2 electrons.
So it gained 2 electrons. Perfect. So did we all make it this far at least? All about the oxidation states. So now we can start breaking them down, of course, into their 2 half reactions. So I'll just start. So we have our chlorine oxide species plus 2 electrons gives us chlorine or chloride. So I have to fix that. Again, I'm just rewriting. And then, so is the chlorine here, is it being oxidized, reduced?
Being oxidized.
I saw reduced in back. So reduced, right? Reduction is gaining. So gained electrons. And so now let's write our other half reaction. So our chromium hydroxide. And then goes to our chromium O4 species. And then, of course, plus 3 electrons. All right, so which side do we want to start with? I guess we can just do the left side, our reduction side. So how do we balance this? What can we do? Sorry? So we will need to do that later, but let's balance out all our atoms first. So keep that on the back burner.
We need to add water to the product side.
So let's add water. So we want to balance our oxygens first. All right, so then if we added water, now we have to balance our hydrogens. So what do we need to do? So H plus on the reactant side. So now I have 2H plus our chlorate species plus 2 electrons gives us chlorine. And, plus H2O, sorry. And then what do we need to do after this? So neutralize with hydroxide, excellent. And so that becomes 2 equivalents of water plus our perchlorate species plus 2 electrons gives us chloride plus H2O plus 2 hydroxide. And so probably at this point, we could do the multiplication that you were talking about. So let's just go ahead and do that since we know we're going to need it. And so it looks like you said times 3, correct? So let's do that now. So going for our common denominator of 6, now times 3, so we'll be ready to add here. So 6H2O plus 3 ClO plus 6 electrons gives us 3 chloride plus 3 water plus 6 hydroxide. All right, so that looks good for our reduction side. So now let's repeat that with our chromium species. So let's see, what do we need to do? Looks like we have 4 oxygens on each side, 2 chromium. So what do we need to do to this? So so how many hydrogens do we need? 4. So 4, so on the product side, right? So let's write that. So our chromium hydroxide species goes to our chromium oxide. Oops. So plus 4 hydrogens, and then of course plus our 3 electrons. And then what do we need to do after adding our H plus? Excellent. So neutralize with hydroxide. So plus 4 hydroxides. Now we have chromium hydroxide plus 4 hydroxide gives us chromium plus 4 waters plus 3 electrons. So now we're here. And then what's the last little bit now we need to do? Yep, so now we're ready to multiply by 2. So 2 equivalents of our chromium hydroxide plus now 8 hydroxide gives us 2 equivalents of our chromium oxide species plus 8 water plus 6 electrons. And so now we just have to kind of rewrite and add. Let me switch colors for a second. So I'm just going to rewrite this top equation again. And so now I'm just going to write our second one. And of course, catch me if I make any errors. Oops, I forgot to write my 8H2O plus 6 electrons. So once we're here, just like before, we need to just start crossing out what's the same on the product and reactant side. And so of course 6 electrons cancels, that's good. And so I'm looking at 6 hydroxide on our product side, and I have 8 over here, so I'm going to cross that out and get 2 hydroxide on the reactant side. And then doing the same thing for water. So I have 6 waters plus 11 or so. So these go away, and then I'm left with 5 on the product side. I think that's it. So now I'll just rewrite it one last time. So 2 equivalents of my chromium hydroxide species plus my 2 equivalents of hydroxide plus my 3 chlorine oxide species, chlorate, gives us 3 equivalents of chloride, plus 2 equivalents of my chromium oxide plus 5 equivalents of water. I had 3 from this one, so 3 plus 8 was 11, and then 6, so 11 minus 5, 11 minus 6, give me 5. And we could have done some simplification earlier in this step, getting rid of the water here and having like 3 and 0, and then that would have left us with 5, but I just saved it till the end. Other questions about this last one? So this is a good stopping point. So Thursday, we'll continue on with kind of electrochemistry and looking at the galvanic cell and cell potential and all that good stuff. So ask questions if you need. And I'm around after class if you need anything. If you need additional help, I'm available. Just make appointments with me. That's best. And like I said, homework, lab, and then you have your quiz, your take-home quiz. Please turn that in. All right, thank you so much. I'll see y'all on Thursday. So I'm going to go ahead and stop the stream in a minute or two. So if you're online, say hi, say bye. And I will see y'all in person on Thursday, hopefully. Yeah, the quiz can go there. And then, yeah, lab, homework. Thanks for coming. Glad to know you were there.
I'm not going to be here on Tuesday next week. We're just gonna do the review. You're gonna.
Yeah, I'll stream it and post the notes after.
Okay.
So you can watch it.
And then I think I lost my take-home quiz.
Up.
Do you have? I might be able to find it.
I can just print out another copy. I gave all of them to Dusty, so I don't have extras, but I can just print a new one.
Okay.
Yeah, so I can do that. Anybody else lose their take-home quiz? Need another copy?
Hang on, I might have it. I totally forgot that was a thing.
What do we have?
I did the redo
Oh,
of the
perfect.
first one, so I didn't know if you needed the first one with it, because it was just the second question that I redid. I don't know if it's too late to turn it in.
No, I'll still take it.
Okay.
Do you?
I just
want
didn't
it?
know, yeah, I just didn't know if you wanted it with it or not, so.
It's not necessary because I can calculate the difference still, but I didn't know if you wanted to hang on to it.
Yeah,
but
I'll hang on to it for now.
Yeah, but I should hopefully get this back to you by lab. But.
Yeah, I do need the take-home quiz.
Okay, I will print some out there, not a problem.
Did you get my paper?
I did, I haven't gotten a chance to read through it, but it is in my possession. All right.
This one here. I think it definitely needs some work.